So let's start with this question, 8.2. And 8.2 says that a rigid tank, that's important, is divided into 2 equal parts by a partition. 2 equal parts, all right? So, I don't know, this is my partition. Ooh, like, ooh. All right. 2 equal parts by a partition. One part is filled with 3 kilograms of compressed liquid water at 400 kPa and 60 degrees C, while the other side is evacuated. So this side we're at vacuum. And this side we have pressure of 400 kPa, temperature of 60 degrees C. So then we have compressed liquid with a mass equal to 3 kilograms. The partition is removed and the water expands into the entire tank until the tank reaches a pressure of 40 kPa. So I know that after we have a P2 of 40 kPa. What is the entropy change in the water? So we're asked to find delta S is equal to what? And we also know, because the tank is split in 2, we know that V2 is going to be equal to 2 times V1. Because when they mean evacuated, they're talking about vacuum. So there's nothing in this half of the tank. Okay. So what we're going to do is we're going to start by looking at state 1. So for state 1, we're told it's compressed liquid, right? So knowing that it's compressed liquid, we know that we can get all of the properties using the property tables, right? We know that specific volume 1 is going to be approximately equal to specific volume F at temperature, which is going to be equal to 0.001017 meters cubed per kilogram. I'm going to see that S1 is approximately equal to SF, which is going to be 0.8312 kilojoules per kilogram Kelvin. Okie dokie. So we're asked to find the change in entropy, and knowing that it's water, right, I can pick values from the table. What I'm going to need is I'm going to need this volume, because I have pressure, but I need some other quantity that I can bring over to this side, right? So with pressure only is not enough to use the tables. I need either temperature, I need either specific volume, I need enthalpy, I need entropy, I need something else to take to the table. And knowing mass and that the volume is twice, I can likely riddle it out. So what I'm going to do is I'm going to start by finding V1. So I know that V1 is going to be I know that V1 is going to be specific V1 times M, which is 0.001017 meters cubed per kilogram, times my mass of 3 kilograms, which will give me a value of 0.003051 meters cubed. I know that V2 is 2 times V1, which will give me a value of 0.006102 meters cubed. Knowing the volume, now I can work backwards and find the specific volume. So I know that the specific volume of 2 is going to be the volume of 2 minus the mass. So my volume was 0.006102 meters cubed divided by 3 kilograms gives me a value of 0.002034 meters cubed per kilogram. Now if I go look at the pressure table, when pressure is equal to 40 kPa, what you're going to see is that the V2 is between VF and VG, which means we have a mixture. Now, what am I going to do with this mixture? I'm looking to find the entropy, right, at that state in order to compute the change in entropy. So what I'm going to do is I need to find the quality in order to relate them. So then I'm going to start by solving V2. I'm just going to list the values here. So I did this comparison and I found that VF was equal to 0.001027 meters cubed per kilogram. And I saw that VG was equal to 3.993. So knowing this, I have all my numbers here. I can compute V2 is equal to VF plus X VFG. Because V2 is known, VF is known, and VFG is known, I can find, with all this information, I'll be able to find my value for X. I'll be able to find the quality of the mixture. So I know that V2 is 0.002034. VF was 0.001027. My quality of X and my VFG, I just do the subtraction. So 3.993 minus 0.001027 will give me a quality of very small. So 0.002523. So like 0.02%, very small, okay? It's very, very small. Meaning that the mixture is predominantly made from water, right? Because we know that a quality of 0 is water. All right, now that I know my quality, I can go ahead and solve for my entropy at state 2. Because I know that S2 is going to be equal to SF plus XFG. And from the table, I can see that I have a value of SF of 1.0259. And my units for, oh, I didn't talk about the units for entropy, did I? So it is kilojoules, hold on, should be kilojoules per kilogram. It's kilojoules, there we go. Per kilo, I didn't talk about it, but it's kilojoules per kilogram Kelvin. Kilojoules per kilogram Kelvin. And my SFG is equal to 6.6441 kilojoules per kilogram Kelvin. Now I'm going to solve my expression for S2. I know that S2 is going to be equal to SF plus X. So X I calculated. And then I'm going to get SFG, so 6.6441 gives me an S2 of 1.0276 kilojoules per kilogram. Now I'm going to be able to find my delta S. Does the question specify total? It just says entropy change, but I solved it and my solution is total entropy change. So it's my delta capital S is going to be equal to M S2 minus S1. So this is 3 kilograms. I have an S2 of 1.0276 minus 0.8312 kilojoules per kilogram Kelvin. Oh, that should be Kelvin. Kilojoules per kilogram Kelvin gives me a value of 0.5891 kilojoules per Kelvin. So that answers all of the components of question 8.1.